Goal for this video is to how to measure the time taken for an object to fall freely and travel through a particular distance. Now, this will allow us to verify the s is equal to half gt square formula, where if we measure the distance precisely, we'll be able to calculate the value of acceleration due to gravity, that is small g. Now, the question arises, how do we measure time? So for that, here we have a relay. It's a simple electromagnetic relay where I've cut off the switch part of it, leaving only the electromagnet exposed, which we're going to use to release a metallic object programmatically. So let's make the connections for the relay. I have 5 volts and ground. So when these two pins are connected, you should be able to find, 5 volts and ground, so there's a thick black wire, that the red light for the LED relay is now on, which means that it's powered on. Now, the third signal wire, I'm going to connect to OD1. As you can see here, it's on. Now, as I toggle OD1, I'm able to toggle the green light, which shows whether the magnet is energized or not. So when OD1 is off, the relay is actually energized, and when it's on, it's off. So there's an inversion there. We just need to bear that in mind. Now let me just move this downwards. All right. Now, if I connect a metallic object here, it should be able to hold it. And the moment I toggle, I can also use the keyboard shortcut T to toggle the relay state. It drops the ball. Toggle it back. Okay. So now, how do we detect that the ball has hit this surface? So this is basically two metal plates which are not touching each other. So if I connect one side to ground, one plate to ground, and the other plate to the sen input, when these two come in contact, sen goes from high to low. So by default, sen is internally pulled up using a 5K resistor, and it stays at 3.3 volts. The moment this touches, you have a falling edge signal detecting when the ball has struck the surface here. So we need to release this, start a stopwatch, and wait for the ball to strike this and precisely measure what the time taken was. So let's take a measurement and see what happens. The shortcut is M, or the measure button here. So I'm getting 193 milliseconds. Let me just go again. Again, 193. 193. So it's very, very repeatable. Millisecond of error, we're getting, okay, 193. So it's see, around 0.2 milliseconds of fluctuations is there if you do this reliably. All right, now that we have a set of readings which are centered around 1.932, let's say, 193.2 milliseconds, let's make some calculations and see if we're getting the distance value. So okay, so I have an IPython window open here. The value that we got was 193.2 milliseconds. So the formula is s is equal to half gt square. So 0.5 into 980 centimeters per second square into t square. So I have 193.2 milliseconds. So let's take into seconds, 0.1932 into 0.1932, which will give me the answers in centimeters because I've taken 980. 18.3 centimeters. So let's verify that. I have the ball here, and the distance should be measured from the base of the ball to where it strikes on the this thing. Okay, so yeah, very, very close. We just touch this to the ground. The base of the ball is here, and yeah, 18.4, roughly 18. Yeah. So the distance is 18.4 as per the scale. We're getting 18.3. So that's very good accuracy as far as I can see. So yeah, that's how you measure time of flight. And there are several improvements you can make to this. Instead of just doing free fall, you can have a ball rolling down a slope. So there, the moment of inertia will factor in, as long as you have a small gradual slope without rolling without slipping. Which can actually consider that this is a solid sphere, and do the theoretical calculations as to how much time it will take, and just the measurement part you can do with just one switch and electromagnet. Yeah, thank you.